Hi everyone, my name is Sabrina binti Rahimi and I will be presenting the first question, question 1. So question 1 asks us to count the sample of race Malay, Chinese and Indians in the dataset. For our first coding, this will read a tab-separated text file into a data frame named diabetes. The header equals to true means that the first line of the file contains column names. The SCP equals to T means values that are separated by tabs. And also, next, the head diabetes will show the first 6 rows of the dataset. The tail diabetes will show the last 6 rows. And the STR diabetes will show the structure, which is the column names and also data types and a few sample values. So the diabetes equals to diabetes stage. All these lines will extract individual columns from the data frame. Diabetes and store them as separated variables like age, BMI, race, etc. And lastly, the table race. This counts the frequency of each unique value in the race column. So hence, on our result from this output, we know that there are 131 Chinese, 75 Indians, and 233 Malays involved in this overall dataset. That totals 439 individuals in the dataset. I'm going to pass question 2 to my friend Natra Suraya.
Hi, my name is Natra Suraya and I am going to continue the presentation. For question 2, to get the range for the variables age, height, weight, BMI and blood glucose in the dataset, we use the command range in bracket and fill in for each variables. The results show that the range for the age is ranging from 90 to 92. Height in the dataset range from 1.32 to 1.93 meter. The weight ranges from 44.9 to 147.4 kg and the BMI ranges from 15 to 56 and the range for blood glucose is 2.68 to 29.2. For plotting the age density histogram, we first use par in the bracket mf row command where C in the bracket 1 to 1 to plot a graph with x and y axis. Use the histogram command in the bracket age main equals to histogram of age for the title of the histogram. Use xlab and ylab command and set x to individual's age and y to frequency. Use the call command to set the color of the histogram and set limitation 10 to 100 on x-axis and 0 to 100 on y-axis using xlim and ylim command. The histogram produced is right skewed, which also means that it's positively skewed. The data is concentrated on the left side of the histogram, indicating that this data set involves those with younger age group, and the longer tail on the right side indicates that the tapering frequency of individuals of older age group.
Hello, my name is Fatin. So for this question, it asks, do the descriptive statistics for the variable age, height, weight, BMI, and blood glucose for the whole dataset race M, C, and I. So first, we will upload the library dplyr, which will load the dplyr package for data manipulation, and then next we will filter the data based on the race needed, where we use the code Malay equals to filter diabetes race and then M. So we will repeat this for Chinese and Indian. Then we will use the summary function to show all the data relevant in each race to be printed. So thus the output will show the summary for each race consisting of the sample, age, gender, height, weight, BMI, race, and blood glucose, so that it is easier for the program to identify and do conclusions. Now I will pass the presentation to Natra.
Hi, so this question asks us to identify the correlation of blood glucose against age, height, weight, and BMI, and asks us to plot a graph for each. So the coding of PAR in the bracket of MF row equals to C in the bracket of 1, 1 will set the plotting layout to 1 by 1 row and column. Hence next, the next coding, the plot age and blood underscore glucose and so on will produce the scatter plot of age against blood glucose, height against blood glucose, weight, and also BMI against blood glucose. So this cor.test function age blood glucose. This function will produce a Pearson correlation test which measures the direction of the linear relationship and the strength between two continuous variables. So the confidence interval is true. Correlation is likely between 0.185 and 0.359, and hence the correlation in the bracket of COR means that the Pearson correlation is 0.274, which indicates a positive but weak linear relationship, and hence there is a statistically significant positive correlation between age and blood glucose. But as age increases, blood glucose tends to slightly increase, and that's also mean that the strength of this relationship is weak to moderate because the R will be equals to 0.274. So the age alone doesn't explain blood glucose levels very well. Same goes to the height against blood glucose plotting, which the output will become t equals to 0.84592, p-value is equals to 0.3981. The correlation R is 0.0404, 95% percentage of confidence level, and hence the interpretation means that the correlation coefficient is very small. It's 0.0404, almost no linear relationship. Hence the p-value is also 0.3981, which is not statistically significant, which is used to be p is more than 0.05. Hence the confidence interval crosses 0 means no meaningful relationship. Hence the conclusion for this plotting is there is no significant correlation between height and blood glucose. Next, the interpretation for weight against blood glucose is also the correlation is positive and weak because R is equal to 0.1836. The p-value is very small, less than 0.001, means statistically significant, and the confidence interval does not include 0, which also means that confirmed significance. Hence the conclusion for this plotting is that there is a significant but weak positive correlation between weight and blood glucose, which also means that heavier individuals tend to have slightly higher glucose level. And lastly, for BMI against blood glucose, the correlation and positive is weak because R is equals to 0.1635. The p-value is significant because it is less than 0.001, means also statistically significant, and the confidence interval is also above 0, confirm that it is a real trend. Hence the conclusion we can get from this plotting is there is a statistically significant weak and positive correlation between BMI and blood glucose. Higher BMI tends to associate with slightly higher level of blood glucose sugar.
For question 5, to conduct a multiple linear regression analysis from the data, we could in multi_reg1 where LM in the bracket blood glucose, age plus height plus weight plus BMI to correlate blood glucose with all the variables. Code in the formula equals to blood glucose tilde age plus height plus weight plus BMI, and use the common summary in the bracket multi_reg1 to get the results of each coefficients, residuals, standard deviations, t-values, and p-values. To plot the graph, use the command par in the bracket mf row equals to c2 and 2 to plot multiple graphs, and use the command plot in the bracket multi_reg1 to plot multiple linear regression graphs. These are the graphs of multiple linear regressions plotted. From the results, the age has the lowest standard deviation amongst all the other variables. This indicates that the dataset did not violate the assumptions made for the linear regressions.
Thank you, Sab, for the presentation. So now for this question, it provides us the value of blood glucose, which is more than 7.0 to be considered as diabetes positive. So which gender have a tendency to have diabetes in the data set? So first, we will load the DPLYR package for data manipulation, and then we will filter the data set with the function male, filter diabetes gender male to include only male patients, and we will repeat for female patients. Next, from the female data set, we will keep only those with blood glucose more than 7 with the function diabetic female, which is filter female blood glucose more than 7.0, more than or equal to 7.0. Then we will calculate the percentage of diabetic females with the equation n row diabetic female divided with n row female multiplied to 100. So the probability of diabetic females will be printed out. So these steps are repeated for diabetic male patients as well. So as a result, we can see that the probability of a male to get diabetes is greater than a female, with the male being 18.18182 and the female with the number 17.85714. Now I will pass the presentation to Natra.
Fabulous. Thank you, Fatin, for the last explanation. And so for this question, they asked us to compare the diabetes prevalence for each race. So the first line of coding will filter all the Malay participants. The second line of coding will filter Malay with blood glucose more than or equals to 7.0, which is diabetic. And the last line of coding will calculate the percentage of diabetics among all the total participants. So this will mean that a total percentage of 9.339408 Malay of the full dataset are Malay individuals with diabetes. We repeat the same coding for the Chinese individuals and also the Indian individuals, and we will get the Chinese with a percentage rate of 5.7% and the Indians of 2.96%. So from this percentage comparison, we can see that Malay have a higher percentage of people affected by diabetes compared to Chinese and Indian. So that's all from me. I'm going to pass this presentation to Natras Raya. We repeat the same coding for the Chinese individuals and also the Indian individuals, and we will get the Chinese with a percentage rate of 5.7% and the Indians of 2.96%. So from this percentage comparison, we can see that Malay have a higher percentage of people affected by diabetes compared to Chinese and Indian. So that's all from me. I'm going to pass this presentation to Natras Raya.
For question 8, can BMI be used as an indicator to predict diabetes based on the dataset? To determine this, we have to get the correlation between blood glucose and BMI. Use the core.test command between BMI and blood glucose and plot the graph by using the plot command, where the variables are BMI and blood glucose. The results shows weak positive correlation, indicating that BMI may determine blood glucose level. And the p-value of the graph is low, hence it indicates that BMI may significantly impact blood glucose. Based on this, it shows that BMI may be used as an indicator of an individual as a diabetic or not.
Thank you, Sab, for the presentation. So now this is the last question, which is exclude the blood glucose less than 7.0 from the dataset and redo the multiple linear regression and compare the results. So first we will create a data frame with the function read data.frame blood glucose, height, BMI, weight, and age. Then we will check the structure using the str function, and then we have to filter the data to exclude the non-diabetic patients by using the negative C function, so that only data from patients with blood glucose more than 7 will be read. Then we will do multiple linear regression for blood glucose based on height, BMI, weight, and age. So display the summary for the multiple regression to get the call residuals, coefficients, significant codes, residual standard error, R-squared, and also p-values. Lastly, we will plot the multiple regression to give us a residual versus fitted plot, QQ residuals, scale location, and BMI plots. So from the results, based on the residuals versus fitted plot, we can see that the spread is more random and the residuals stay closer to the zero line. For the QQ residual plot, we can also see that the points stay closer to the diagonal line and the points are evenly distributed around the line. The plot also has less curvature, which is a better fit to normality. So that is all from us. Thank you.